We will begin our next lecture on the finite element methods. And in this lecture, we'll be talking about the advanced rod elements and requirements for the numerical solutions. Well, in the previous lectures on the rod elements, we got to know that we are writing the displacement function of the rod u as a function of x is equal to shape function 1 and 1, which is a function of x, multiplied by the nodal coordinate u1. u1 was the value of the displacement at node 1 plus n2 as a function of x u2. Fine. Now, in case of these n1 and n2, we know n1 is equal x2 minus x divided by L1 or divided by length of the element, and N2 is equal x minus x1 divided by length of the element, right? Now, as far as these shape functions N1 and N2 are concerned, we can obtain these shape functions from what are known as the normalized Lagrange polynomials. That is, if we talk about the normalized Lagrangian polynomials, we can obtain these shape functions from normalized Lagrangian polynomial. Okay, how? The question is how we can obtain these shape functions n1 and n2 from the normalized Lagrangian polynomial. Well, as far as the Lagrangian polynomial is concerned, the Lagrangian polynomial is defined as Li as a function of x of order n is equal x minus x1 in x minus x2 into x minus x3 so on into x minus x I minus 1 into x minus x plus I plus 1 plus so on. Oh, sorry, in the last term is x minus x, and we know from the numerical techniques this is what we call as the Lagrangian polynomial, and this is in fact how we properly define this Lagrangian polynomial. Now, if we normalize this Lagrangian polynomial, then its normalized form, we'll write it slightly like this: Li normalized Lagrangian polynomial as a function of x can be written as it's written as Lin as a function of x divided by Li n xi, and that is further written as, in terms of the product notation, j going from 1 to n, where j is not equal to I. It is x minus xj in x minus xi. Okay, this is the method of writing this normalized Lagrangian polynomial, and this is well known by the students who deal with the numerical techniques. Fine. And in case of the finite element methods, we define it as sorry, I have just a minute. I will be drawing it here, so that will look quite sensible from here. Okay, I'm sorry, it has got deleted, so I will redo my. I will rewrite the equation. I was talking about the normalized Lagrangian polynomial Li and I as a function of x is equal, in terms of product symbol, write this as j going from 1 to n and with j not equal to I, this is written as x minus xj divided by x minus xi. That's how we write it. X minus xj divided by x minus xi. Let us open it up. Okay, that is, we write our shape function ni as a function of x is equal to normalized shape function l I n as a function of x. Okay, uh, for a two-noded element, for a two-noded element, for a two-noded element, we can write it that our j goes to 2. Okay, we can write normalized shape function li n as a function of x is equal uh, j going from 1 to n. N is the number of nodes, so we have 2. It's x minus xj divided by x minus xi. Okay, so when I is equal to 1, so it will be, therefore this will be x minus x2 divided by x minus x1 in multiplication with x minus x1 divided by x minus x2. Okay, that's it. So this we call as, this is one of our shape function, that is what we call as n1, and this is another shape function that we call as n2. Okay, so this is how we obtain our shape functions n1 and n2 in terms of the this, what you call as the Lagrangian polynomial, in terms of the normalized Lagrangian polynomial. So we can definitely state that as far as the Lagrangian polynomial is concerned, the Lagrangian normalized polynomial is the representation, is a way of representing our these what we call as the shape functions. That's why these shape functions are also called the Lagrangian shape functions. Okay, that's why these C naught continuous elements, the shape functions, that this shape function that we have discussed, or the previous shape function that we are presenting by n1 and n2, they are also known as the Lagrangian shape functions. Okay, we'll be talking more about their conditions that they must satisfy. They're also known as the C naught continuous shape function. Okay, we'll be talking about the C naught continuity, what it means in terms of the derivatives, okay, in terms of integrability. Okay, but what's very important that they see this n1 and n2 shape functions are also known as the Lagrangian shape functions. Okay, they are also known as the Lagrangian shape functions. They are also known as a C naught continuous shape function. We'll be talking about the C naught continuity. This is very important. We need to know about it. But this is quite important to represent these shape functions in terms of these Lagrangian shape functions. Okay, apart from this representation, we can also talk a little bit about the what is known as the parametrization of the shape functions. Okay, that is, we write in terms of a natural coordinate system, writing shape functions in terms of the natural coordinate systems, in terms of the natural coordinate system, in terms of the natural, writing shape functions in terms of the natural coordinate system. That is very important for us. How do we write these shape functions in terms of the natural coordinate system? So what we do, we define a coordinate system. Just a minute, please. We define a coordinate system. Let us draw a line. Let's suppose we are having an element. This is the node of the element. This is another node of the element. This is node 1 and this is node 2. This is node 1 and this is, say for example, node 2. Okay, now we define a coordinate system where the origin of the coordinate system lies at the center. Okay, So we define it by zeta. Okay, so here at the center we say zeta is equal to 0, and here at the left hand zeta is equal to -1, and here zeta is equal to +1. We define the natural coordinate system whose value ranges from -1 to 1 passing through 0. And at any point within this, so initially we were talking about x coordinate system, that's the global coordinate system. Now we are talking about the natural coordinate system whose value ranges from -1 to 1. We define the zeta is equal 2 times um, 2 times x minus xe divided by L. So what is this x minus xe divided by L? This xe is the coordinate of the center. Okay, so uh, at this very point, at the midpoint, you see that x is equal to xe, therefore zeta is equal to 0. And if we look at the value of the xc over here, this is the value of x here is x1, isn't it? And the value of x here is x2. Fine. So at this very point, zeta comes out equal 2 times x1 minus xc divided by L. Fine. So if you look at this, is xc minus x1 is minus L by 2. So this is minus 2 L by 2, and we have L that comes out equal -1. That's here. That is this element we are saying from here to here in terms of natural coordinate system. We assume that its length is 2. Okay. Similarly, if we have now, if we are defining our natural coordinate system by this formula, fine, then if we take we will write this Lagrangian coordinate system, Lagrangian normalized polynomial in terms of zeta now. Okay, Lin, not as a function of x, but now as a function of zeta, will be equal j going from 1 to n, number of nodes, zeta minus zeta j divided by zeta minus zeta I. Okay, zeta minus zeta j, zeta I minus zeta j, zeta I minus zeta j. Fine. In the previous case, we have to make a correction. Fine. This is how we define it. Now, let's suppose we have a two-noded. If we have a two-noded system, two-noded element. If we take a two-noded element, okay, so we'll be having Li to zeta is equal product j going from 1 to 2 e minus zeta j divided by zeta I minus zeta j. Fine. That will be equal, that is zeta minus zeta I, zeta minus so we'll start from, if I will take the first value 1, then zeta will have to go to 2, because I should not be equal j. J is not equal to I. Okay, I grows from 1 to 2, so first value I takes is 1, therefore j should take the value 2. All right, zeta 1 minus zeta 2 in product with zeta minus zeta 1 divided by zeta 2 minus zeta 1. Okay, so we will definitely define that as far as our two shape functions is concerned, the first shape function n1 as a function of zeta is equal zeta minus zeta 2 divided by zeta 1 minus zeta 2. Okay, and that can further be written as zeta minus zeta 2 divided by zeta 1 minus zeta 2. If you look at zeta 1 is equal plus 1. So it is zeta minus 1 divided by zeta 1 is equal minus 1 this is minus 1. That comes out equal 1 by 2, 1 minus zeta. This is one of the shape functions in terms of n1, and n2 as a function of zeta will be equal, if you look at the second shape function n2, that is equal zeta minus zeta 1 divided by zeta 2 minus zeta 1. That is zeta 1 is minus 1, so it will be 1 plus zeta. That is zeta 2 is 1 minus 1, that is plus 1. That is 1 by 2 into 1 plus zeta. Okay, so if we write the two-noded element, in terms of zeta, then the shape function here will be n1, that is 1 by 2, 1 minus zeta, and here the shape function will be 1 by 2 into 1 plus zeta. This is if we write these shape functions in terms of what you call as the natural coordinate system. Now if we have a three-noded element, have a three-noded element, okay, with three nodes, if we take into consideration the three-noded element, that's called a three-noded quadratic element. If we take a three-noded quadratic element into consideration, briefly, if we go back in terms of x, that will be u as a function of x is equal to alpha naught plus alpha 1 as a function of x plus alpha 2 x square. Okay, if we take this element into consideration for an element having three nodes, okay, if we have a single element but having three nodes now, 1, 2 and 3, this is node 1, this is node 2, and this is node. What about this element? How you will write the shape function in terms of zeta? In terms of zeta, if we have to write it, okay, we will simply write that lin as a function of x j going from 1. Now we have three nodes, so it will be 1 to 3, where j is not equal to I. Okay, j should not be equal to I. Now we have three elements, so it will be equal zeta minus zeta 2 divided by zeta 1 minus zeta 2. This will be the first term. In multiplication will be zeta minus zeta 1 divided by zeta 2 minus zeta 3, and the last term will be zeta minus zeta 3 divided by zeta 1 minus zeta 3. Okay, so with I j not equal to 1, okay, j goes from 1, I goes from 1 to 3. Fine. So the first shape function for a three-noded element will be, so we'll write n1 first shape function as a function of zeta. Since we have three nodes, we'll be having three shape functions. So first of the shape function we can write, that will be n1, that will be zeta minus zeta 2. It will not be having the first term, that is zeta minus zeta 2 into zeta minus zeta 3 divided by zeta 1 minus zeta 2. Okay, because it is zeta 1, zeta I minus zeta j. So that's why this will be zeta 1 minus zeta 2. Zeta 1 minus zeta 3. Okay. Now n2, the second shape function as a function of zeta, will be equal, second shape function will be zeta minus zeta 1 divided by zeta 2 minus zeta 3 multiplication with zeta minus zeta 3 divided by zeta 1 minus zeta 3. And the third shape function, zeta 3, I will write here n2 as a n3 as a function of zeta will be equal zeta minus zeta 2 by zeta 1 minus zeta 2 into zeta minus zeta 1 by zeta 2 minus zeta 3. Okay, now be careful about these shape functions. So these are the three shape functions n1, n2, and n3 in terms of zeta. We can still solve them. I mean to say, we can write them as if you take the element with three nodes into consideration, we have the element is like this. There's three nodes. So at the center, we have to place our coordinate system. So here is zeta, this is zeta 1, this is zeta 2, this is zeta 3. Zeta 3 will be equal to plus 1, zeta 1 is equal to minus 1, and zeta 2 is equal to 0. If we substitute our over here, we'll get n1 as a function of zeta is equal to our zeta 2 is equal to 0 and zeta 3 is equal to plus 1. So it will be in the denominator, in the numerator, it will be zeta into zeta minus 1. Okay, divided by zeta 1 minus zeta 2. Zeta 1 is equal to minus 1 into zeta 2 is 0, zeta 1 minus zeta 3, that is minus 1, minus zeta 3 is 1. Okay, that will be equal 1 by 2 into zeta into 1 minus zeta. Okay, that is the first shape function. So the first shape function will come out to be equal in terms of zeta is equal n1. The first shape function n1 as a function of zeta is equal 1 by 2 zeta into 1 minus zeta. Okay, similarly the second shape function as a function of zeta will be obtained, and we can also obtain n3 as a function of zeta. Okay, so we can obtain these shape functions in its terms, and this will be equal 1 minus zeta square, and this is equal 1 by 2 into 1 plus zeta into zeta. We can do it the same way as we did it. This is how we write the shape functions in terms of the natural coordinate system, that is zeta. Similarly, we can talk about an element having four nodes. If we have a four noded element, we have a four noded element. So be careful, element does not have only two nodes. We can have three noded element, we can have four noded element. Okay, let's divide it into a single element having four nodes. Okay, four noded element. So second node, this will be third node, and this will be fourth node. So for us, this is node 1. Let me write it here: node 1, node 2, node 3, and node 4. At the center, we have to place our coordinate system, that is here. This is zeta. At this end, we have to say zeta is equal to minus 1. At this end, zeta has to be equal to plus 1. Okay, at the center, zeta is equal to 0. So what will be the value of zeta over here and the value of zeta over here? Fine. So in order to find the value of zeta as, so we have zeta 1 is equal to minus 1. We have zeta 4 is equal to plus 1. We have zeta, we have to find the value of zeta 2, and we have to find the value of zeta 3. That can be easily found. See, we are dividing this length into how many parts? 1, 2, and 3. We can write a general formula for it, which in this case we can write zeta is equal 3 times x minus xc divided by length of the element, because here the length of the element is 1, 2, and 3. When we normalize it, the total length will be equal to 3. That's why we are writing 3. So at x2, zeta will be equal 3 times x2 minus xc divided by the length of element, that is L. Okay, that is equal 3 times x2 minus xc. Let me slightly draw it down. That is x2 minus xc. For the two elements, therefore we can write it as, let me clean the space, sorry, it can therefore be written as, let me, we are having four nodes, sorry, so we can therefore write it as, we have four nodes. This is node 1, this is node 2, this is node 3, and this is node 4. Our zeta stands over here, so we are still dividing this entire into two elements. We can therefore write zeta is equal 2 times x minus xc divided by length of the element. Total length of the element is L. Okay, so at here at this point zeta is equal to -1. Here at this point zeta is equal to +1. What is the value of zeta at x equal to x2? That is 2 times x2 minus xc divided by L. x2 minus xc, the total length is L. This from here to here it is L by 3. From here to here it will be L by 6, but it will be minus L by 6. And we have our L, and we have in multiplication will be 2. That is -1 by 3. So here zeta is -1 by 3, and here zeta is +1 by 3. So based on this, we can therefore write our shape function formula in terms of the normalized Lagrangian polynomial, that is Li up to n as a function of zeta is equal to the product term j going from 1 to n, where I is not equal to j, and this is zeta minus zeta j divided by zeta I minus zeta j. So our j in this case will go from 1 to 4. Okay, therefore the total shape functions will be, if we start writing j going from 1 to 4, we can therefore write these shape functions n1, n2, n3, and n4, the quadratic shape function. So this is how these shape functions are written. Apart from these shape functions, what we have to do now is the concept of the parametric interpolation. That is something very important that we have to slightly talk about, the parametric interpolation. And very essentially, we have to talk also about the numerical integration that hopefully we'll be doing in the next video. Thank you.